Hello, my name is Gib Bernhardt, and I'm pleased to be the host for Conversations about Geology. In 1978, I first visited Yaquina Head and became fascinated with the clatter of the cobbles moving in the wave's swash. I returned to Newport, Oregon in 2012 and began teaching at Oregon Coast Community College. So nearly 40 years later, I realized what a perfect topic for this second broadcast would be: one small rock on a rocky beach. On my Facebook page, Conversations About Geology, I have set up a picture album to accompany this radio broadcast. The following sounds are the actual sounds of the Yaquina Head cobble beach that once again triggered that memory. What is even more fascinating is how one small rock is a weathered culmination of an epic journey that began deep underneath southeastern Oregon and northern Nevada, eventually erupted in central southeast Washington, flowed across both southern Washington and northern Oregon, down an ancestral Columbia River gorge, and flowed through Salem and on towards Yaquina Head, eventually stopping at Seal Rock, Oregon. The type of rock forming Yaquina Head in Newport and Elephant Rock and Seal Rock is igneous. Igneous rock is any rock that has cooled down and crystallized after being molten. Yaquina Head is a mafic igneous rock. Mafic rocks have relatively low concentrations of the mineral silica and high concentrations of the minerals olivine and pyroxene. There are two basic types of mafic igneous rocks, gabbro and basalt. Gabbro is an intrusive rock, a rock that slowly cools from a magma melt within the earth. It cools so slowly that the minerals that make up the rock have time to crystallize to a size visible to the eye. Basalt is the extrusive form of the mafic rock, meaning it has erupted onto the surface of the earth. Because basalt cools so rapidly in the atmosphere, its minerals are microscopic, not visible to the naked eye. Basalt is the rock that forms Yaquina Head and Elephant Rock. Indeed, they form a large portion of the surface rocks seen in eastern Oregon and on the Columbia Plateau. Because of the low silica content of mafic lavas, they contain less gas and flow easily as sheets of lava spreading across the surface of the earth. Basalt magmas are derived from the mantle. Researchers Coffin and Eldholm use the term large igneous province or LIPs to describe very large accumulations, areas greater than 38,610 square miles, approximately the area of Iceland, of mafic igneous rocks that were erupted or emplaced at depth within an extremely short geological time interval, a few million years or less. There are three theories proposed for the formation of the Columbia River flood basalts, LIPs. 1. Plate-related stress formation. 2. Meteor-induced formation. And 3. The widely accepted plume formations of LIPs. Plate-related stress formation is a model in which ruptures are caused by plate-related stresses, such as formed the Basin and Range province of North America. The stretching and thinning of the crust in the Basin and Range fractured the lithosphere, the crust, and the very upper mantle, allowing melt to reach the surface from shallow mantle sources. The high volumes of molten material that form the LIPs are postulated to be caused by convection in the upper mantle. For the meteor-induced model, 7 pairs of hot spots in the LIPs located on opposite sides of the Earth have been noted. The hotspot pairs include a large igneous province opposite an oceanic hotspot. On impact, seismic waves would propagate around the world and converge close to the antipodal position. As the waves focus on the antipodal position, they put the crust at the focal point under significant stress, rupturing the crust. The rebounding shock wave creates a deep rising plume of mantle material. There is no antipodal hotspot opposite the Columbia River LIPs. The most widely accepted theory, and one that works well with the basin and range plate-related stress model, is the idea that a single superplume of rising hot mantle material originating near the outer core is ascending to the base of the lithosphere. Rock in the plume, though solid, is plastic enough to flow and rises buoyantly because it is less dense than the cooler mantle rock surrounding it. When the hot rock of the plume reaches the base of the lithosphere, it starts to melt and produces magma. When the plume that produced the Columbia River flood basalts, the Yellowstone plume, intersected the lithosphere, it broadened and spread north and westward. As the North American continental plate moved westward, the broad head of the plume was sheared off by the thick edge of the Precambrian cratonic lithosphere, and the plume head moved northward. The plume minus the head continued eastward towards Yellowstone. Today, the greatly thinned northward moving plume head still lies beneath Oregon and abuts next to the eastern edge of the High Cascades. There are two main petrologic forms of basalt. One, tholeiitic basalt, a silica-saturated basalt that contains the minerals pyroxene and low-calcic plagic clays. And two, alkaline basalts, a low silica-saturated basalt that contains olivine and calcic feldspar. Most tholeiites are formed at approximately 30 to 60 miles depth within the mantle and are typically associated with flood basalts on continents and ocean floor basalts erupted originally at mid-ocean ridges. Alkali basalt magmas form at greater depths, perhaps as deep as 90 to 125 miles, and are typically found on updomed and rifted continental crusts and on oceanic islands such as Hawaii, Madeira, and Ascension Island. The Columbia River Basalt Group is a large igneous province that lies across parts of the western United States. It is found in the states of Washington, Oregon, Idaho, Nevada, and California. During the Middle to Late Miocene epoch, the Columbia River flood basalts engulfed about 63,200 square miles of the Pacific Northwest, with an estimated volume of 41,800 cubic miles. Eruptions were most vigorous from 17 to 14 million years ago, when over 99% of the basalt was released. Feeder dikes form the vents for the flood basalts, and the rifts trend to the north-northwest across eastern Oregon, Washington, and western Idaho. The vent systems are from 30 to more than 125 miles long and less than a mile wide. The largest accumulations of feeder dikes is the Chief Joseph dikes in the Tri-Corner area of Oregon, Washington, and Idaho. As the plume head moves northward from southern Oregon and spreads westward, the age of the basalt decreases in age. The Columbia River Basalt Group consists of 5 major formations. From oldest to the youngest, they are the Steens Basalt, Immanha Basalt, Grand Ronde Basalt, the Wanapum Basalt, and the Saddle Mountains Basalt. The Columbia River Flood Basalt Province comprises more than 300 individual basalt lava flows that have an average volume of 120 to 140 cubic miles. The flow that makes up the Yaquina Head and Elephant Rock on the Lincoln County coast is the Ginkgo flow of the Frenchman Springs member of the Wanapum Basalt Formation. This flow has been dated to 15.6 million years before present. Coupled with the shear plume hypothesis is the delamination or peeling off the bottom of the mantle lithosphere. The mantle plume beneath southeast Oregon caused drip-like delamination of the mantle lithosphere that mixed with the decapitated plume head, generating the Steens basalts beginning 17.5 million years ago. As the plume spread northward, the delamination of the mantle became slab-like, and the plume rose to the upper lithosphere at the base of the crust, generating both the Immanha basalts about 16.5 million years ago and the Grand Ronde basalts between 16.5 and 15.6 million years ago. Finally, the plume collided with the craton boundary, melting the much older crust with sporadic eruptions of the Wanapum basalts between 15.6 and 14.5 million years ago, and Saddle Mountain basalts between 14.5 and 6 million years ago. The individual flows varied but locally the combined layers reached a thickness of 8,000 to 9,000 feet. Sheet flows require large volumes of mafic magma that are extruded rapidly, typically from major fissures or feeder dikes, as in the case of the Columbia River basalts. Such large volumes and rapid eruptions require very large shallow magma reservoirs under enormous pressures. The final cooling and hardening phases of each flow produce several characteristic layers, each distinguished by a core and top. The core is divided into a lower colonnade with undulatory columnar and blocky joining, a metal entablature with fanning columnar joining on the bottom, and slender columns on the top of the core. The top is a vesicular lava, meaning holes caused by escaping gas, with brecciated angular fragments and an undulatory surface. The smooth, rounded basalt cobble I found on the beach at Yaquina Head is from the Ginkgo flow. The Ginkgo is one of 6 flow units of the Frenchman Springs member of the Wanapum Formation of the Columbia River Basalt Group. The Ginkgo flow erupted between 15.6 and 15.3 million years ago. Nearly 384 cubic miles in volume, 310 miles long, and covering more than 14,286 square miles, the Ginkgo is one of the largest flows of the Columbia River Basalt Group. At the head of the flow, in the central Columbia Plateau and Pasco Basin, the Ginkgo is 100 to 200 feet thick. In the ancestral Willamette River Valley, the Ginkgo forms an intra-canyon flow 300 to 500 feet thick. The basalt at the terminal end at Yaquina Head contain hyaloclastites. A hyaloclastite is a hydrated, tuff-like breccia, rich in black volcanic glass, formed during volcanic eruptions either underwater or in water-saturated sediments. It has the appearance of angular flat fragments sized between a millimeter to a few centimeters. Ho and Cashman characterized the Ginkgo flow, determining that it had been formed in roughly a week. This was based on the measured melting temperatures along the flow from the origin to the most distant point of the flow. The Ginkgo basalt was examined over its length from the Ginkgo flow feeder dike near Calotus, Washington, to the flow terminus in the Pacific Ocean at Yaquina Head, Oregon. Their research indicated that the basalt had a maximum temperature drop along the flow of 68 degrees Fahrenheit. Analysis indicate that the flow must have remained laminar, as turbulent flow would cool more quickly. Basalt sheet flows travel at velocities ranging from 3 to 26 feet per second without turbulence. In addition, the Ginkgo basalt flow marks the oldest course of the Columbia River. The Ginkgo flow veered at the Dalles, followed an intra-canyon pathway. Part of that river channel is buried under the much younger and later emplaced Mount Hood of the High Cascades. The flow then curved towards Salem and onward towards Yaquina Head at Newport. Subsequent basalt flows over the next 3 million years forced the Columbia River to near its present position. By Miocene time, marine sedimentation was confined to areas close to the present-day shoreline. The Miocene shoreline was perhaps about 5 miles inland compared to today's shoreline. The Ginkgo flow following the ancestral Columbia River would eventually invade the Newport embayment, forming the coastal features at Yaquina Head and Seal Rock State Recreation Site. Since Miocene, continued uplift and erosion have destroyed the evidence of the channel between the Ginkgo flow observed at Salem and the Ginkgo flow examined at Yaquina Head. Because of the vast amounts of gas released by such large volume eruptions, flood basalts have the potential to impact the global climate. It has been estimated that gas plumes extended 2 to 7 miles above fire fountains and fissures. Based on a study of gases released from the younger Raza flow, 9,000 metric tons of sulfur dioxide was released. These amounts are enormous relative to well-studied historic eruptions. For example, the 1991 eruption of Mount Pinatubo produced 20 metric tons of sulfur dioxide. The impact of these eruptions was thought to be severe, possibly causing mass extinctions. For example, the amount of sunlight reaching the surface would be reduced to the equivalent of full moonlight. However, 5,000 to 10,000 years may have passed between eruptions, allowing the environment to recover. There are three formations that crop out in the vicinity of Yaquina Head: the Oligocene Yaquina Formation, the late Oligocene to early Miocene Nye mudstones, and early to middle Miocene Astoria Formation. The oldest of these formations is the late Oligocene Yaquina Formation. The formation is of deltaic origin, containing thick to thinly bedded sandstone, glauconitic sandstone, conglomerate, and tufaceous siltstone sedimentary rock. They are commonly cross-bedded with foreset bedding and have scour and fill structures. Lying over the Yaquina Formation is the late Oligocene to early Miocene Nye Formation, found along the shoreline from just north of Seal Rock, Oregon, to Yaquina Head. The Nye Formation is a dark, olive-gray, organic-rich, deep marine mudstone and siltstone. The general finding upward sequence indicates a transgressive sequence, a rise in sea level, during the late Oligocene to early Miocene. One of the best exposures of the Nye Formation is found at the Vietnam Veterans Memorial at Nye Beach. The third formation found along the coast near Yaquina Head is the Astoria Formation. Astoria sedimentation began in the early Miocene and continued into middle Miocene. These are thick to thin-bedded, very fine to medium-grade, micaceous and carbonaceous orcosic marine sandstones and sandy siltstones. Best exposures are at Moolock and Beverly Beach. The sandstone and siltstones show bioturbation in a nearshore marine environment with some of the richest Miocene fossil beds on the Oregon coast. The coarsening of the sediments from the Nye Formation to the Astoria Formation at this locality indicate a regressive sequence or a fall in sea level. At Yaquina Head, the ginkgo flow consists of subaerial and invasive basalt lava flows and flow breccia. What are invasive lava flows? Due to its high density, basaltic lava may burrow into unconsolidated sediments, wedging the sediments up and over the flow. At the terminal end of the ginkgo flow, the basalt flowed down a submarine canyon and wedged into the Astoria Formation and rests nonconformably on the Nye mudstone. Erosion after uplift removed the softer surrounding Astoria Formation from the top and sides, and leaving an inverted landscape of the actual flow of the harder, more dense ginkgo basalt that was within the channel. The extreme southern terminus of the ginkgo flow is found at Seal Rock State Recreation Site, where the dominant feature is Elephant Rock. The upper basalt rests nonconformably on top of the Oligocene Yaquina deltaic siltstone sandstone. I hope you have enjoyed this program about one small rock on a rocky beach. If you are interested in learning more about the geology of the Pacific Northwest, please consider taking my geology courses at Oregon Coast Community College. It would be wonderful to meet you there. Until next time, please remember that something as insignificant as a small black cobble on a rocky beach has a history of epic proportions, and that the future of our planet can only be predicted from the evidence we have discovered from the past. I wish to close by saying to go outside, take a walk. The world is a beautiful place, and only our curiosity can make that beauty meaningful. So long.